Good afternoon, CB154. My name is Jeffrey Ha, and I will be presenting Group 3's Quantitative Analysis in the Sequence Inversion Kinetics Lab. Heterogeneous catalysis is widely used by chemical engineers on the industrial scale to accelerate naturally slow chemical processes. And the heterogeneous catalysis are employed in packed bed reactors, which are very effective chemical reactors. Our focus in this experiment was to use spherical catalyst pellets for the sucrose inversion lab, which is an exothermic first-order reaction between sucrose, glucose, and fructose. Our team's main goal was to understand the effects of reactor temperature and pellet size in sucrose conversion. And our methodology is the following. We used Amberlist 120 as our solid catalyst, which is made of several cross-linked polymers with protons on them. These protons serve as the active sites to catalyze the hydrolysis of sucrose and can be found on the surface as well as inside the pellets. We considered two different pellet diameters, 0.31 millimeters and 0.88 millimeters, which is shown in the appendix. And by flowing a sucrose solution through the packed bed reactor, we obtained a glucose and fructose-rich solution, in which the concentration was obtained by using spectrophotometry. To accomplish our goal, we altered relevant variables and recorded the optical absorbance of our product, and we will explain our findings and conclusions throughout the whole presentation. To understand our packed bed reactor, our team performed a differential mass balance. The reactor feed is an aqueous sucrose solution, denoted as 1 here, while the reactor exit stream, denoted as 2 here, comprises fructose, glucose, and any other reacted sucrose. Here we have an extra stream at T equals residence time tau, and Z equals reactor length L. We can find the relationship between radial position and concentration of the sucrose on the surface of a single pellet. In common scenarios, there are mass transfer limitations, both inside and outside the pellet. This leads to deviations in concentration at different positions, such as bulk, surface, and inside the pellet. To simplify our model, we made assumptions of no external mass transfer limitations, and thus no boundary layer. First, we assumed steady state flow in the PBR, no temperature gradient in isothermal reactor, and also no external mass transfer limitations, where there is no concentration dependence with radial position outside the catalyst pellet. And we can denote this assumption as omega equals to 1. While acquiring the governing equation for a reactor, we defined eta as the effectiveness factor, in which we will explain later. And while we cannot assume eta to be equal to 1, we can find the following governing equation between conversion and residence time and reactor constant for the first order reactions. Our team analyzed the glucose product in order to determine the effects of pellet sizes and temperature. We first defined conversion as the following equation, as the glucose in the product over the initial sucrose in the feed. And this is because the stoichiometry relationship was 1-to-1. According to collision theory, reactant particles must collide with each other with sufficient energy and favorable orientation for reaction. And here, catalysis provides suitable domains, also known as active sites, that minimize activation energy barriers of the reaction, and hence increasing the reaction rate. Theoretically, smaller pellets and higher temperatures result in a faster reaction rate as well as a higher conversion. This is attributed to the fact that as pellet sizes decreases, the surface area to volume ratio increases, and thus there are more access sites accessible. Also, as temperature increases, effective diffusivity increases and allows more reactant particles to reach active sites inside the pellet and overcome the energy barrier to react. Information on the effective diffusivity is provided in the appendix. Data collected from our experiment agrees with our theory, from the collision theory, as using smaller pellet yielded a higher conversion compared to that of larger pellets. To physically understand the packed bed reactor and their operating conditions, it is essential to introduce two dimensionless numbers. First, the Thiele modulus, denoted as capital Phi, and second, the effectiveness factor, denoted as eta. Both of the equations provided in the presentation are only applicable to first-order reactions. Here, the Thiele modulus is a ratio between reaction rate and diffusion rate within a pellet, while the effectiveness factor is the reaction rate ratio between just the surface of the pellet and the entire pellet. When we plotted both numbers against temperature and pellet size, we found an opposite dependence between the two numbers. While Thiele modulus increased with temperature, the effectiveness factor decreased with temperature. And to further understand this trend, we have to define the two regions of the Thiele modulus. So when the Thiele modulus is greater than 1, it is it's a diffusion limited reaction in which the rate determining step of the whole reaction is highly dependent on the sucrose molecule diffusing into the pellet rather than the actual reaction. When we see that all the data points that we collected in an experiment are in the diffusion limited region, as shown in the left plot. Larger Thiele modulus values implies a reaction significantly limited by diffusion, and this behavior is widely observed in larger pellets. Due to the greater internal mass transfer limitations, larger pellets exhibit smaller effectiveness factor values. And this makes sense because for larger pellets, internal mass transfer limitations affect the overall rate more than the overall rate more, and the overall rate is much slower than the surface reaction rate. Based on the plots shown in the last slide and the plot that we can see here on the right, smaller pellet sizes are very incentivizing to be implemented into PBR systems. For larger pellets, there are a lot of internal mass transfer limitations, and this hinders sucrose molecules from accessing the internal active sites in the catalyst. On the contrary, for smaller pellets, we observe much faster reaction rates because we are the particles are able to access these active sites more, access better, I guess. Thus, we can see that if we had to choose between the two, we would definitely choose the smaller pellet because, from an industrial standpoint, a faster rate would lead to higher conversion and ultimately a larger economic value, since we are trying to sell glucose here. And according to our experiment, further decreasing the pellet size so that the kinetics and the diffusion rates are equal should be ideal. By using this Goldilocks catalyst pellet size, we would be able to maximize the sucrose conversion rate. So in a nutshell, these observations on the right clearly show that the smaller pellet sizes are much more beneficial than larger pellet sizes in terms of conversion. Based on the PBR governing equation, our team extracted the true rate constant values for the two pellet sizes according to the Arrhenius equation. Here, the exponent. Here, A is the pre-exponential factor, and the exponent, also known as the Boltzmann factor, determines the fraction of sucrose molecules having sufficient energy. Using the calculated rate constants, we plotted a log plot between K and the reciprocal reactor temperature, and in which the exponential regression equations can be found in the appendix. If we go to our plot of true K, we see that there are two equations for the rate constants, and they're slightly different. Since rate constant should be a single value, because it's not dependent on internal mass transfer limitations, we can average these two sets and get a single average true rate constant equation. This is a good approximation, as shown on the right, because our true activation energy is actually very similar to literature value. The apparent K value is given by the effectiveness factor multiplied by true K, and in this plot, we plotted the apparent rate constant trend alongside with the average true K trend. Because the effectiveness factor is always less than 1, or always less than 1 in isothermal assumptions, we see that the apparent rate constants are lower than the true rate constants. And by finding the slope of the log plot, we computed the apparent activation energy, in which 60.1 kilojoules per mole was the activation energy for the 0.88 millimeter pellet. Although our team is slightly skeptical with this value because we expect larger diffusion constraints to increase measured apparent activation energy. We decided to go with this value. Based on the activation energies found in the previous slide, our team modeled a packed bed reactor operating at 80 degrees Celsius with a pellet diameter of 1 millimeter. The following two plots show the conversion in sucrose concentration as a function of position along the reactor. And although these models may not be the most sophisticated due to extrapolation and large propagation errors and also many assumptions that we made, they do accurately describe the overall effect of using heterogeneous catalysis in a PBR for a sucrose inversion reaction. And by using the catalyst, our team was able to provide an alternative reaction path with lower activation energy, increasing the Boltzmann factor significantly. Remember that the Boltzmann factor is a fraction of particles with sufficient energy, and that fraction increasing by the power of 10 to the 7 is huge. Further increasing apparent rate constants will accelerate the reaction, and ultimately this will lead to a higher conversion and decreased exit stream sucrose conversion, as shown in the green plots, under the green lines in the two plots. While our modeled PBR exhibits a conversion of 0.44, using smaller pellets should further increase conversion. And this basically agrees with the conclusion that we made earlier in the presentation that smaller pellets are much more favorable for reactor use. Our team also modeled a continuous stirred tank reactor, denoted as Cstr, operating at the same conditions as the PBR earlier. While a packed bed reactor only assumes perfect radial mixing, a Cstr assumes a homogeneous mixture in which the exit stream's composition is equivalent to the overall composition of the fluids inside the Cstr. And it is noteworthy to point out that a PBR is basically an infinite number of Cstrs in series, each with a differential size. And based on our governing equation for a Cstr, which we developed and it's also shown in the appendix, our team was able to derive the conversion rate for the Cstr. And here we see that even at the same operating conditions and reactor size, the Cstr can only convert 1/3 of the feed sucrose into our desired product compared to the 0.4. The difference in conversions can be attributed to the fact that a Cstr is a well-mixed reactor everywhere and is very dilute, thus requiring more residence time for a complete reaction. In reality, it is not always certain that smaller pellets are most optimal to use, and we should also reconsider the merits of using a large catalyst pellet. In order to do this, we must first understand the Ergon equation, an equation that represents the relationship between pressure drop and fluid flow in fluidized or packed beds. And when the fluid flows through a PBR, frictional forces and increased vertical position, because usually PBRs are vertical, they cause head loss, and this ultimately decreases the pressure of the fluid. To understand the Ergon equation in this relation to our experiment, this is the Ergon equation, but we're now going to show an analog of the Ergon equation. And it turns out that the super small catalyst pellets can cause a significant pressure drop due to the inverse relationship between diameter and pressure drop. And here, the pellet diameter is denoted by d sub p. In industrial scale settings, under predicting, the pressure drop is undesired, and this is because retrofitting the chemical process can be quite expensive because you might need larger pumps and stronger compressors to compensate for the pressure drop, or you need to empty and refill the whole column itself, which is very expensive. And thus, this is very important to consider that a pellet that is not too small. It is important to consider a pellet that is not too small, has good performance, but does not cause this issue on a large scale, which is basically the Goldilocks operation condition motive that we're focusing on. After looking at the multiple facets of this laboratory experiment and detailed data analysis, we conclude that designing heterogeneous catalysis requires one to consider a wide variety of factors, not just conversion. And so throughout this experiment, we observed that the lowering of a reaction's activation energy is possible using heterogeneous catalysis. And our team also modeled a PBR operating at a specific temperature with a large pellet size and realized that although our model wasn't very sophisticated, we were able to learn the relationship between temperature, diffusion, kinetics, and conversion. For smaller size pellets, higher conversion rates were observed, and this is mainly attributed to the minimized mass transfer limitations. And although superficially it seemed like the smaller pellet sizes were the way to go, upon literature review, we also learned that larger pellets might be incentivized due to the undesired pressure drop existing in PBRs. Hence, we conclude that an ideal catalyst design is very situational. To holistically improve our experiment's accuracy, one can replicate our experiment and minimize random error in our empirically discovered values. Also, a more rigorous model can be acquired by eliminating the assumptions we made about the system. It is also important to link our learnings from this experiment to industry. And while Amberlist 120, the catalyst that we used in the experiment, was very effective and provided highly effective catalysis for sucrose inversion, it is also important to further develop far more effective catalysts, and currently researchers are conducting a lot of experiments on porous materials such as metal organic frameworks, denoted as MOFs here, and zeolites to maximize product yield. Additionally, computational research is widely conducted, and usually these methods are used to accurately locate active sites on a catalyst and also to understand optimal operating conditions for various catalysts. Thank you, professors, and for listening to our presentation, and I guess we can open the board to questions.